Afternoon. So today we will start discussing our main algebraic tool to be used in this class, the notion of a vector. I'm not sure if I mentioned before, but I will say it again, and probably I will say it repeatedly while we are going through this this introductory part or the first part of the course. If by any chance you studied vectors, the basic operations with vectors, the definitions, and so on and so forth, you can certainly skip faster or even skip entirely these first lessons before we actually get into the specific calculus-specific part of the material. However, if by any chance this is the first time you actually encounter this notion of a vector, and it's the first time when you learn about things like the dot product, cross product, and so on, you really want to go slow and make sure you take your time. It may seem like we spend too much time on this introductory part, but if you really understand well how these main algebraic tools work, it'll be much easier to understand the calculus-specific part that makes use of these tools, because they will be used quite often later on. So what is a vector? So there is a formal algebraic, abstract algebra definition of the notion of a vector, but in our class it's sufficient to just go over a very intuitive way to describe this this entity if you want, and via some examples, and then move quickly to properties and operations. So roughly speaking, a vector is a mathematical object, a very loose or encompassing word. So it's a mathematical object that has a magnitude or indicates a magnitude and a direction. Of course, without some examples that may not mean much, right? But basically any physical entity that requires or that encapsulates automatically a magnitude of some sort and a direction of some sort can be represented by a single mathematical object called a vector. So there will always be some default examples that we will use in this class, and default examples of vectors that will come up quite often are the velocity, for example. The velocity is a vector, because remember, not to be confused with the speed that tells you how fast you go, how fast a mobile goes, but a velocity indicates also the direction of motion, right? So this indicates direction of motion and speed. And obviously the easiest way to visualize this type of vector is with an arrow. That's why geometrically we represent vectors by arrows, and we attach their physical meaning depending on the context, right? So for example, if I move, if some car, let's say, moves or travels north, let's say northeast, 60 miles an hour, maybe I'm going to represent that by this arrow. If another car moves or travels south, let's say this is, like I said, 60 miles an hour, right? 30 miles an hour, but south, I'm going to indicate that with an arrow that is half as long as the previous one, pointing downward, right? So that'll be the velocity vector for a car that moves due south with 30 miles an hour. Another easy or familiar example to keep in mind, which you probably know from physics courses, is a force. Right, again, has a magnitude and a direction, because, for example, let's say you have a sled. I'm not good at drawing, so just imagine this is a sled, right? And then a kid pulls the sled with a certain force, but at a certain angle. Then, of course, you're going to represent that force with an arrow to indicate the direction of the application of a force, and the length of the arrow to indicate the magnitude of that force. So, with that out of the way, obviously, and I already mentioned with these examples, obviously the default way of representing, or the typical way of representing a vector, is by an oriented segment. its length denotes the magnitude of the vector, and of course the 2 points of the segment will indicate the direction. So let's write a generic example. Let's say you have a point of coordinates x1, y1, z1, and then the point B of coordinates x2, y2, z2. And then we have to indicate an arrow, at one of these points so that together between A and B we indicate the direction of this vector. So the typical notation in this case for a vector will be by specifying the initial point. So this guy here, A, is called an initial point of the vector, and B is the terminal point. So a typical notation for a vector in this case, if I want to represent it by a variable, if you want, is by specifying the initial point, the terminal point in this order, and an arrow on the top. So I hope you guys agree that the notation is quite suggestive, because just by looking at this notation AB with the arrow on the top, I can tell immediately which one is the initial point, which one is the terminal point, and the arrow on the top indicates the direction from A to B. All right, so let's actually write down a very important remark at this point to keep in mind, which again deserves another color here to emphasize its importance. There is no unique representation. There is no unique geometric representation of a vector. When we talk about the direction, make sure you do not confuse the location of a segment with the actual direction, right? So for example, going back to the example with the car here on this corner, if I say the direction is north-south, northeast, there are lots of arrows that you can indicate that direction, northeast, right? Let's say I don't care about the magnitude, right? So I can northeast, if I don't specify anything else about the problem, there are infinite many arrows that you can indicate that direction, right? And again, if I want to have them all with the same magnitude, you can clearly see that a vector does not have a unique representation. So more to the point, to go back to the generic example here on the top of the remark, if I have, let's say, another vector parallel to A and B with the same magnitude, so let's say, let's see if I can fit it here, on the top here, let's assume that this guy here from C to D is gonna be of the same magnitude with A and B and parallel. So if they have the same magnitude, excuse me here, magnitude, and then parallel, they represent exactly the same vector. So the vector from C to D, it's exactly the same vector from A to B. No unique representation, and actually you can, it doesn't really matter which representative or representation of a vector you can choose. The whole math will work just as well. Now, this may seem quite confusing. This seems like an overly complicated stuff, like, that's something that makes the life more miserable than easier. But there is a blessing in disguise, in the sense that precisely because of this remark that there is no unique representation, we can choose a more convenient representation. And the most convenient one is the one that places the initial point at the origin. The one with the initial point at the origin of the coordinate system. So what that means is, let's say, let's sketch our coordinate system here, x, y, z, and let's say my my vector A and B is over here. Let's say, as before, x1, y1, z1, the initial point, and then x2, y2, z2, the terminal point. I can choose to translate A and B. So imagine I start from the origin and I draw a vector which is parallel to A and B. Let's again use a different color here. So parallel to A and B, and let's say the terminal point here is M. And by the way, whenever you want to move a vector to a different position, so by keeping the magnitude and the direction, you could do this by simply subtracting the points, the coordinates of the initial point to place it at the origin. So you want to move A into the position of the origin. That means essentially subtracting, to achieve this, that means subtracting the coordinates of the initial point. This is essentially a translation of the segment. You want to translate the segment, you basically you essentially want to translate the segment by the amounts given by the coordinates x1, y1, and z1. So, and you do that for all the points in the vector, including the terminal point. So that means, while the origin, of course, now is 0, 0, 0, M now becomes x2 minus x1, y2 minus y1, z2 minus z1. We're going to go over some examples in a moment. And by the way, we're not going to do this operation too often because it's more convenient to start with the vectors already starting from the origin. But again, if by any chance, let's say you start with a vector with an arbitrary initial point and arbitrary terminal point, and you want to bring it so that the initial point is at the origin, algebraically that means subtracting the coordinates of the initial point from all the points on the vector, including the terminal point. Now, the advantage of this representation is that now, and let's use different variables. Let's say now the difference between x2 minus x1 is A, y2 minus y1 is B, and z2 minus z1 is C. So the advantage is now the vector now can be represented just by the coordinates of the terminal point. And by the way, this is a special notation. This is the so-called component form of a vector. We're going to go over lots of examples in the next page in a minute. But again, just to recap on this page, we have, I have to switch this to the black color again. We have an arbitrary vector with an arbitrary initial point and terminal point. By bringing the initial point to the origin, by making this translation, we can now represent the vector using only 3 quantities. That's the main advantage. So instead of keep tracking with of 6 quantities, the 3 coordinates of the initial point, the 3 coordinates of the terminal point, now we can track only the coordinates of the terminal point because automatically we know that the initial point is at the origin. This is the most practical form of representing a vector, and I'll have more to say on this after we go over a couple of examples on the next page, so stay tuned. All right, so let's take a quick example. Let's say we have a vector from P to Q. We're not going to even bother to sketch it. P is of coordinates, let's say 1, 1, 2, and then Q of coordinates 3, 2, 1. And we want P, the vector from P to Q in component form. Again, that means essentially placing P at the origin. So P becomes the origin. And visualize the coordinate system, how you translate P and Q. But algebraically, that means every point is translated by subtracting 1, 1, and 2, right? So the new terminal point, so the new vector, let's say from the origin to another point M, is with M being given by 3 minus 1, 2 minus 1, 1 minus 2, right? So you subtract the coordinates of the initial point from the terminal point. So 2, 1, and minus 1. Okay, so because the component form of a vector always starts from the origin, we're not gonna need to specify the origin as the initial point all the time. So another notation for a vector vector in component form is a small variable with a bar on the top and or less greater than brackets to specify the components. These are the notations we're going to use most often, right? So this vector in component form from O to M, let's say we can denote it by little u, right? That's another notation for a vector in component form. So our vector from the origin to the new point M can be denoted by another letter with a bar on the top, or and or the brackets which will specify the coordinates of the terminal point, which are 2, 1, and -1. So just to keep in mind to avoid any confusing of notation here, so let me put this as another remark here. Do not confuse a point with a vector. Okay, so once again, if I want to refer to the actual terminal point, then that's specified by parentheses, right? Like you specify any point, 2, 1, -1. So in general, if you have round parentheses between, around some coordinates, these basically denotes a point, right? So you denote a point in 3D by specifying its coordinates. So the notation familiar that you have from previous classes, right? If you are in 2D, in 2 dimension, you have only 2 coordinates. However, now if I use this notation, 2, 1, -1, so same number, same coordinates, this denotes the vector that starts at the origin and has M of coordinates 2, 1, -1 as the terminal point, right? So 2, 1, -1 can denote the vector itself in component form. 2, 1, -1 can denote the actual point. Again, I'm insisting on this because there will be some problems later on in which this type of confusion may pop up. I mean, there are problems in which, for example, some points are given, some vectors are given, you have to manipulate some of those quantities, and it's extremely important to not make a confusion between whether you actually see or are given a point by its coordinates, or you're talking about a vector in component form. Okay, so enough with so many preliminaries. Again, like I said, the good news is that from this point on, we're going to use vectors in the component form. Now, it's important to point out that you're not going to physically draw them at the origin. So in other words, if you have a picture, let's say you have some sort of motion, right? And you have an object here that moves on a path. And there are various quantities that are represented by vectors denoting this point. Let's say you have some force here, some velocity. And let's say you have some acceleration, which is another vector, right? Which denotes another quantity that has a direction or a magnitude, and so on and so forth. Notice I use the notation in the component form because that is the form that you use in computation. It's the most convenient one, but you don't actually need to physically, when you sketch this picture, to actually translate all, take all the vectors that you have in the relevant in the problem and actually sketch them at the origin. Although the component form denotes a vector that starts from the origin, in the figure, you do not actually need to make this translation. Otherwise, you're going to have a hedgehog here, like arrows pointing in all sorts of directions coming from the origin. And that's not going to help, right? So you still place the vector on the picture where it is suggestive, right? So I mean, if it's a velocity of an object, I'm going to place that vector at the object here where I put it in the figure, despite the fact that in computation, I'm going to use its component form, which comes from translating the vector at the origin, but that translation doesn't need to be drawn on the figure. So with that being said, let's actually move on to the next page and talk about some basic operations with vectors and some other definitions. Well, actually, before we do that, let's actually do another quick definition. We're going to talk about scalars. A scalar, for our purposes, is just a real number, which begs the question, why do I call it a real number? Again, that comes from the more abstract definition of a vector space in abstract algebra. But for our purposes, basically a scalar is just a quantity to not be confused with a vector. It's a real number, but the scalar can be associated with a vector. Because like I said before, a vector can have does have a magnitude and a direction. So very often we may need to actually extract the magnitude of a vector. So for that we have a special notation. So let's say we have a vector U of components A, B, and C. Again, this comes from Pythagorean theorem as well, or the distance formula if you want. The magnitude of a vector of a vector U is denoted by the absolute value. We're going to say magnitude of U because it's a vector, but we're going to use the symbols that you use for absolute values, which is square root of a squared plus b squared plus c squared. So that's simply from the Pythagorean theorem geometrically. But of course, in practice, it may denote whatever the magnitude is appropriate in the question, right? So for example, if we talk about a velocity, the vector that indicates speed and direction, how fast you go and where you go, the magnitude of this vector is going to be the speed. So the magnitude of the velocity is also called a speed. There is also a good reason why actually the absolute value is used for the magnitude and for the absolute value for real numbers. We're going to get to that maybe later, but there is no risk of confusion because it's all depending on the context, right? So I mean, if I put a vector which is clearly indicated by this notation between absolute values, then clearly I mean the magnitude of a vector, not the absolute value of a number. On the other hand, if I have absolute value of -7, let's say, then obviously this is 7, right? I mean, that's going to be the absolute value of a real number, so that means something else. So keep in mind the context matters because often in the same computation, you're going to have both an absolute value of a real number and the magnitude of a vector in the same computation. So let's move on to the next page. All right, so some other basic definitions. Once we have a vector v, we can define what is called the opposite of vector v, of the vector v, and that's going to be denoted by -v, and is going to be the vector with the same magnitude as v, but in the opposite direction. Okay, so in other words, if we were to sketch it, if this is v, then the one which will have precisely the same magnitude but in the opposite direction, you can denote that by -v. So they have the same magnitude, and we can state that using our notation for the magnitude. Now, let's move on now to some basic operations for vectors. And in this section, we're going to talk about scalar multiplication. So let's talk about vector operations. And we're going to talk about some motivation why we have these. All of these operations arise because of necessities in real life. Okay, so I mean, for example, why do I care about the why do I define something called the opposite of a vector? Well, you know, obviously, if you want to talk about, let's say, a mobile that all of a sudden turns around, I mean, moves in the opposite direction with the same speed, then how do you represent that quickly, right? Because you have the same magnitude, but then you want to represent it by that the direction is the opposite that it was before, like 180 degrees, right? So minus the opposite of the original vector makes sense to have that meaning. Scalar multiplication, the first operation we're going to talk about, has to do with manipulating the magnitude of a vector with the magnitude of a vector, yes, with or without changing its direction depending on the case. So the scalar multiplication, as the name implies, this is an operation defined between a scalar. So suppose C is a real number, again also known as a scalar, and V is a vector. Then C times V, sometimes I put a dot here, but I'm not gonna actually I'm gonna try not to actually use the dot, because a very emphasized dot will be for a different type of operation, and it's better to just use the convention from real numbers that if I don't specify anything between the two variables, then that's essentially the multiplication. Although this is not, of course, the multiplication between numbers, because this is the multiplication between a real number and a vector. And the result is going to be a vector. So what is CV? What is this scalar multiplication? This is going to be a vector whose magnitude is absolute value of C times the magnitude of V. And in the same direction as V, if C is greater than 0, and opposite direction if C is less than 0. And here's a quick example geometrically, and then we're going to show how to do this on paper, how to actually compute the coordinates of the new vector. Let's say this is V, the original one. Let's see, I don't actually have enough room here. Let me actually do it here. So suppose this is V, and then same direction but twice the length. For example, this could be 2V, right? So same direction but twice the magnitude. Or if I do it this way, let's say I count 3 magnitudes in the opposite direction, this will be, for example, minus 3V. At this point, we're going to mention that we also define the null vector, the vector with coordinate 0, 0, 0, which is basically the vector with no magnitude or 0 magnitude. It is necessary, of course, to make the algebraic rules for vector operations complete. So that's one of the necessities of this. Another notation for the null vector is 0 bar, to indicate that we talk about a vector of coordinate 0, 0, 0. And by convention, of course, 0, the scalar multiple by any other vector, that's going to be the 0 vector, right? So the vector with 0 components, no matter what vector you multiply by 0. Now, how do you actually define this? How do you compute the scalar product? Many operations with vectors are quite intuitive, and this is one of them. Not all of them are intuitive, but as an example, well, let's actually state it in the general rule. If we have a scalar C and a vector V of coordinates x naught, y naught, z naught, then CV will be the vector of coordinates cx naught, cy naught, cz naught. So each coordinate is multiplied by this C, by the scalar C. Component-wise multiplication. So as an example, if I have to multiply the scalar 2 by the vector 1, 1, 2, that's going to be 2 times 1, 2 times 1, 2 times 2. Obviously, you could do it much faster once you understand how the operation works. So this is 2, 2, 4. And obviously notice that the magnitude of 1, 1, 2 is square root of 1 plus 1 plus 4, which is square root of 6. And as expected, the magnitude of 2 times 1, 1, 2, which is 2, 2, 4, is going to be square root of 4 plus 16, which is square root of 24. But it's very easy to see that this really comes from 4 times 6. So that's, as expected, twice the magnitude of the previous one. So the fact that C makes modifies the magnitude, again, we can state this as a general rule. Magnitude of C times V, C scalar multiple V, is the absolute value of C times magnitude of V. Again, I can't emphasize this enough. Pause the video if you need to. How important it is to understand which operation you're talking about depending on the context. Between C and V here, this is not the regular multiplication. This is a scalar multiplication that we just defined. And this is the magnitude of a vector. Right? The symbol, the absolute value. On the right hand side, this is the regular multiplication. Because you multiply a real number by another real number. Remember, the magnitude of V is a real number on its own. Right? And these are just absolute values. The absolute value of C. Whereas here, these bars are again denoting a magnitude. Okay? So same notation means something different depending on the context. Again, it's going to be really easy once you practice a little bit with the homework. It's not going to be a big deal because the context is always the one that dictates what we're talking about with each operation. I'm going to say something more about the scalar multiplication on the second page, and then we're going to continue with vector addition. And that'll be the last topic of the day. So stay tuned for the next page. So scalar multiplication can be used in reverse to pull out common factors from coordinates. So as another example, let's say you have a vector of coordinates 16, 8, minus 24, let's say. It might be more practical to pull out as much scalars as possible via a reverse scalar multiplication. So I can notice that 8 is a common factor, if you look carefully, right, of each coordinate. So then I can basically write the whole thing in reverse by pulling out 8 as a scalar in front of the vector. This is something that is going to pop up also often in some contexts. So essentially, as a rule of thumb, which I'm going to mention it later, keep scalars out of the vector if possible, right? In the computation, final answer doesn't matter as much, but in computations, you might notice that things may become easier if you do just that. Because then if you have to do, say, cross products or some other fancier or more complicated operations with vectors, it pays off to have easier coordinates to deal with, or smaller numbers. Let me think a little bit if we should mention it here. I think it's probably worthwhile to mention it here, although it's going to come up later, and let me actually do it with a different color because that's also important. Scalar multiplication is also used to create a vector of length 1 or magnitude 1 from a given vector. So from a given vector. This is also called normalizing a vector. So let me emphasize what I'm talking about. Let me illustrate what I'm talking about with an example. Let's say we have a vector u of coordinates 3, 1, and let's say -1. Now the magnitude of u is square root of 9 plus 1 plus 1. That's going to be 11, right? Square root of 11. Actually, let's see if we do, I was thinking about something. Well, we'll leave it at that. I was thinking to do some nice numbers, but I don't think it's necessary at this point. So what if I want a vector of length 1 in the direction of u? Well, the way to do it is the answer to that question is to multiply. Sorry, let me start over here. So the answer is to multiply u by the reciprocal, by 1 over its magnitude, by the reciprocal of the magnitude. In this case, 1 over square root of 11. So by scalar multiplying a vector with 1 over its magnitude, you effectively create a vector of length 1 in the same direction of u, right? So in this particular case, that'll be 1 over root 11 scalar multiplied by 3, 1 minus 1. You can bring it inside, you don't have to, but by doing that, automatically this vector will have length 1. I mean, it's very easy to see why that's the case. We don't have to use Pythagorean theorem again. I mean, what is the magnitude of 1 over square root of 11, 3 scalar multiple 3, 1 minus 1? Remember, we don't have to do we can use the definition of the scalar product, which states that the magnitude of this is going to be the absolute value of 1 over root 11 times the magnitude of the vector 3, 1 minus 1, which we already established is root 11. Okay, so it should come as no surprise that the new magnitude is 1. The reason why we want to do this is going to be a little bit more obvious as we move along later, but at this point, let me just state that, roughly speaking, you may want to do this whenever you want to preserve the direction of a vector and to prepare that vector later, maybe for manipulation of the magnitude for a different number. Like, for example, let's say I want to use that direction and create various vectors of different lengths. Then you can simply multiply by the new scalar that indicates those new magnitudes. But generally speaking, you can think of it as a standard magnitude. So if I want essentially a bunch of vectors that encapsulate direction only, as a standard, because you could choose essentially any length you want, right? If you want to preserve the magnitude. But as a standardization process, if you want to have them, all of them as at length 1. Have these standard vectors of length 1 that indicate various directions of interest. And you can always make them any length you want later by multiplying it to a scalar which denotes that length. That's the advantage of normalizing. But again, the application of the context will become clearer later. I just put this here because that's an immediate application of the magnitude of a vector, of a scalar product, sorry. So let's finally move on to define the sum of the two vectors, the other operation of vectors, or vector additions. And I'm going to use, again, a definition which is very intuitive, geometrically speaking. So given u and v, two vectors, we're going to define u plus v in the following way. If the initial point of v coincides to the terminal point of u. This is going to sound strange when you put it in words, but the picture is gonna be much more suggestive. So if the initial point of v coincides to the initial terminal point of u, then u plus v is the vector that has the initial point of u and the terminal point of v. So I put it in words because we need to have like a formal definition of some sort, but in practice, I mean, intuitively, if you sketch what I just said here, and again, you can take a break to make sure you write this down. Here's how the operation works, and then we're going to immediately talk about why you may want to invent such an operation, like what is it good for, in other words. So let's say you have a vector u over here and a vector v over here, right? Because notice the definition may sound a little bit too restrictive, because what if the vectors don't start the way I mentioned in the definition? What if v doesn't start at the terminal point of u? But remember, there is no unique representation of a vector. You could always translate the vector v to any position you want. So you're going to move it here and then make it so that it starts from the terminal point of v, of u, sorry. That's going to be the same vector v, right? Parallels, same direction, same magnitude. And then once you place them according to the definition, then u plus v is going to be this, this vector that connects the initial point of u with the terminal point of v. If you want an immediate application, you can think of it as the cumulative effect of, let's say, a bunch of forces. Let's say, for example, you move an object according to various forces applied at different points on the motion. One here, and then continue with this force here, and then another force over there, and so on. So the cumulative effect of these forces is going to be essentially the sum of these vectors. In physics, you also talk about the resultant force, right? When you apply various forces to an object, the sum of them is the overall effect of these forces on this object. There is another way to represent geometrically the summation of two vectors. That's when you put the two vectors to start from the same origin, from the same original point. This is the so-called parallelogram law, because to represent the summation of the two vectors, you form a parallelogram between the two vectors. So you make them start at the same initial point, you form a parallelogram, and then the diagonal that starts from the same original initial point of these vectors will be the sum of the two vectors. These two definitions are equivalent, because notice that, again, if I translate v all the way to the terminal point of u over here, then you recreate the definition that I mentioned in words. Once again, the good news is that you don't need to sketch anything in order to actually compute the summation. You can sketch it if it's useful for the problem at hand, but to actually compute the summation, that's another operation which is quite intuitive to perform, which we're going to show on the next page. All right, so let's take a generic example. So if you have a vector of coordinates x1, y1, z1, another vector of coordinates x2, y2, z2, then the sum of the two turns out that has the components x1 plus x2, y1 plus y2, z1 plus z2. So again, it's one of those intuitive operations in the sense that they act component by component, right? I mean, if someone will ask you to guess how you define such an operation, you may guess that you add component by component. Now, keep in mind that not all operations are intuitive. We'll get to that on the next lesson. But for now, let's enjoy this aspect of the material. So let's take an example. let's say I have a vector of coordinates 1, -1, and 5, and v of coordinates -3, 2, -3, let's say. Then u plus v will have coordinates 1 plus -3. Again, you could do this faster, but I want to emphasize how you do the component-wise addition, 5 plus -3, right? So then you end up with -2, 1, and 2, right? So that's going to be the vector which represents the sum of the two vectors. And then, so yeah, so let's actually make at this point just a couple of more examples later, but let's actually have a little summary of all the properties or operations we encounter so far. So once again, given u x1 y1 z1 v x2 y2 z2, what did we which relevant operations and quantities we talked about? Well, we talked about the magnitude, which comes from the distance formula. We talked about the opposite of a vector. So let's say minus u, that's going to be minus x1 minus y1 minus z1. And obviously the magnitudes are the same between the opposite and the original. We talked about the scalar product. Cu, if C is a scalar, that's going to be Cx1, Cy1, Cz1, with the more important property that the magnitude of Cu is the absolute value of C times the magnitude of U. And then finally the summation of the vector addition, which is essentially component-wise addition of these coordinates. Remember, for R2 is the same except you don't have the third coordinate. All of these operations are the same. So just a couple of more things to cover. I mean, just one little thing. This I don't actually like that as much, but it is important actually in many applications. I mean, whenever I have a choice, I prefer not to use this notation, but there is something called a standard basis in a vector space, let's say in R3. And let's actually see where this comes from before I actually talk about what it means. So let's actually start with an example. So notice that no matter which vector you start with, so let's say I start with 3 minus 1, 5. I can actually use in reverse the vector addition and scalar multiplication in a very specific way that shows pretty much any vector can be written as a linear combination of three important vectors, which form that basis I was talking about. So notice I can split it first into a summation of three vectors, each of which keeps one of the coordinates and leaves 0 for the other two coordinates. Again, take a moment. If you want, you can pause the video and make the vector addition from right to left, and I hope you convince yourself that this equality is true, right? So you can split it into a vector addition by having 0 coordinates everywhere except one coordinate. Furthermore, now because I have those zeros, I can actually pull out each of these coordinates using again a reverse scalar multiplication. 3, 1, 0, 0 plus minus 1 scalar multiple with 0, 1, 0 plus 5 scalar multiple 0, 0, 1. And I hope it's not hard to realize that doesn't matter which vector you choose, you can you can do the same process, and you're going to be able to represent that vector as this linear combination of scalar multiple of coordinates a, b, c, and these somewhat special vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. So a basis in a vector space is essentially a set of vectors that can be used to represent any other vector. So it turns out that these special vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 can be used to represent can be used to represent any vector. And because of that, they form the so-called standard basis. They have a special notation. I is denotes 1, 0, 0, J with a bar on the top to indicate that's actually a vector, 0, 1, 0, and then K, which is 0, 0, 1. So from this point on, you have a choice to write a vector in the component form, either as a vector by specifying the coordinates in these brackets, or as a linear combination of the standard basis. And in some cases, it might be advantageous to write it as a linear combination of I, J, K. These are unit vectors as well, right? Because their magnitude is always 1. That's another important thing to keep in mind, which may come up later. I usually prefer to write it like that if I have a choice, but like I said, in some cases, this notation is necessary. So let's move on with another example. Let's say in reverse. Suppose I have a vector u of written like this: 4i minus 3j plus 2k. That's the same as the vector in component form 4 minus 3, 2. Keep in mind that the absence of one of these ijk means that its coefficient is 0. So let's say, for example, I have 2i minus 4k. That means j has the coefficient 0, right? So that means its component form is 2, 0, minus 4. I should also mention that the R2 version of the standard basis contains obviously only two vectors, 1, 0 and 0, 1. There is no k vector. There's no third coordinate. Okay, so I think that is enough for today. We're going to continue the next lecture with slightly fancier vector operations, after which we could do far more. We can actually talk about actual applications, far more interesting than what we just mentioned up until this point. So that's it for today. We'll see you next time.